On to our last topic, the idea of force and pressure, and how integrals can be used to determine these things. Well, we're not going to do any example problems this one. Our next and the last video, we'll do an example, but we need to understand what the heck is going on. So let's jump into it. Force and pressure. So pressure is a force per unit of area. And we're going to deal with newtons per square meter. So we're going to want to think kind of like a lot of our games are going to be like, you've seen a dam before, right? You know, a dam blocks water. We want to know how much pressure is on that dam. You know, how much does it have to hold up? You know, most of you are going to be engineers or something. Not most of you, but a lot of you are going to be engineers and stuff like that. You're going to be building things that's going to need to withstand pressure and force. So in order to build something, you need to make sure that it can withstand that much pressure and or force. So do you know that just hanging out in the world, there's pressure on you. There's atmospheric pressure. On the surface of Earth, it's approximately just hanging out. It's 10 to the 5th Newton meters squared. What is that? What's the fifth? 1, 2, 3, 4, 5. 100,000 newtons per square meter. Wow, okay. Or if you want to talk about it, we could say, have you ever heard about pounds per square inch? Or like, you ever heard of PSI? Ever heard of PSI? So on Earth, it's approximately 14 pounds per square inch. That's just being a human. That's what's being exerted on you at all times. But we're going to stick with the SI units or the metric system as we go through these problems. So let's move on and let's go with a little assumption. Let's assume you're at the bottom of a swimming pool. You're at the bottom of a swimming pool. But we're going to make it simple. We're going to think of it as this, that you look like me. You're basically two-dimensional. You know what I mean? You're at the bottom of a swimming pool. Oh, maybe the pool's like this. Well, let me make it actually. Golly, come on, I suck. Not remaking this. I'm going. So let's say there's some swimming pool with water in it. You know, there's a little bit of water up here. And you're at the bottom of the swimming pool, but you're going to be like me. Two-dimensional. You're just a straight line. I'm telling you, I turn sideways. You can't even see me. I'm that skinny. Maybe not as much anymore. I got a gut now, so it sticks out. All right, not the point. We're going through, so we're going to think of ourselves as merely being flat, and we're at the bottom of a swimming pool. Maybe it's like you threw, I don't know, some round, maybe threw a weight into the swimming pool, fell down to the bottom, and then we know that above you is all this water. There's a new pressure. You ever dove down to the bottom of a swimming pool and your ears start to feel all pressurized and stuff? Because, yeah, the further you go down, the more pressure. It's all of this water on top of you pushing on you. So we're going to say that surface area down here, we're going to call that A. You know, there's some area on it because while you're flat, I mean, if we were to do this more three-dimensional, you would have some area at the bottom of the pool. Cool. So that area would be in meters squared. So how is this going to all relate? Well, it's going to relate in this manner. Well, you have the water above your head, right? You have your water above your head. There's some sort of height to this. I'm trying to draw three-dimensionally. You know what I mean? We don't care about the water that's to the right of you or to the left of you, but this has some sort of height. All right, there's some sort of height, some h meters above you. So let's talk about the force that's being put upon you. The force, well, we know that that's mass times acceleration, right? We have that down from before. And then what was mass? Do you remember this from our last one? Well, that's going to be your volume times the density of water. Well, we know that to be something or other. times the gravity, our acceleration. Well, the volume of the water, well, wait a second. That would be A, the base, that area, times H, however high it is. So we could go through and replace that. So I'm like, oh, okay, cool. So our volume is, it's that A times the H. And then we have our density, which is just rho. Yeah, we could call it 1,000 times G. Cool. We found the force. Awesome. Look at us go. But wait a second. Here we go. Here is pressure. If we don't remember, it's all good. We just learned this. But pressure is going to be the force divided by whatever the area might be. But we found that area to be A. And our force was this A times the height times our rho G. Well, come on, look at that. It just goes away and we get the height times the pressure times the force of gravity. And this is what we're going to call hydrostatic pressure once we start doing our problems. So our pressure, one more time, is H times rho times G. We're going to use this in a second. So now we're moving into this idea of hydrostatic pressure. Hydrostatic, not moving, pressure. Okay, so hydro, water, static, not moving. That's static. It means it's not moving. So water, not moving, pressure. So what we're thinking is possibly this is the side of a dam. And there's water on the other side of it pushing upon it. And it needs to be able to hold it. So the game is it has the same magnitude at all directions since the water is at rest. But there's a height of this thing where isn't there going to be a little bit more pressure down lower? I mean, I know that's moving down, but how do we set this thing up? And I'm going to kind of stay away from a lot of it. I'll let you, I may link a YouTube video to somebody that understands this a little better than I do. I mean, I get it, but I don't know. I'm not professional. I don't know all the tricks through it. Well, let's look. So we look at one strip, as always. We got one strip, and it's delta y long. We're saying that this dam is A units high, right? And we always want to set up our xy as such, right? You want to keep your xy like that. It's nice to have the bottom being there, but you can set it up any way you want. As always, you are allowed to do more work rather than less work. We're like, well, what's the pressure on the strip? Well, of course, it's got to be that rho G, right? That rho G. It's just all about the height. It's just all about the height. Well, we're going from A, and I hope we're getting this by now. It's A to whatever any Y value. A minus the Y. Whatever the height is, minus the Y value. So the force on the strip is going to be, well, it's that pressure times the area of said strip. Well, the area is just the width. I know we kind of have it blocked now, but it's the width times that delta y. And that will create the force. And we're not looking for work any longer. We're just looking for force. So we can say we got that some F sub K, just the force on the kth strip is going to be, oops, I always want to write rho as, so rho times G times that A minus the Y sub K. This here is the pressure. And then we need to multiply by the area of said strip, which is the width of Y sub K times delta Y. And that's the area of the strip. And I hope you know what's going to come next, since I think we have a couple more of those strips. Oh, we can say that the total force will be approximately the sum as k equals 1 up to n of our f of k's. I'm not writing that whole thing in there again. Let's not do that, huh? Let's not write it all in. We know what it is. So we're going to say that our force is equal to the limit as n tends towards infinity of the sum from k equals 1 up to n of our force for one freaking strip, which is going to tell us the force is equal to the integral from 0 up to the top, our rho g, those constants of a minus our y value, the depth, times the width, dy. Now I'm going to tell you the big issue. What's going to end up happening is the width is going to be some sort of x values, but we need it all in terms of y. So that's going to be the tough game that we're going to approach. So this will be our formula for hydrostatic pressure. Again, rho and g, we will just rip them out. When we take tests, we'll look at it this way instead. We'll take out that 9,800 because the density of water is still 1,000. Gravity is still 9.8 meters per second squared, or it's actually negative, but we're going to be going the opposite direction. So whatever the top is, minus y, times the width. The game will be finding the width. So in the next one, we'll do an example problem. We'll run through this whole thing, and we'll see what's up so you can be successful on your exam. Now, these types of problems, before we get into it, you only have a 20% probability of seeing one of these, a 1 in 5, a little lower. But please make sure to do your homework. I don't expect we'll see it, but the only reason we'll see this on our midterm is if people don't do these problems. If I notice no one's doing these problems, don't worry. If you show up to the meetups or stuff like that, or in class, I'll tell you, hey, nobody's doing these problems. And that's going to be key to you to go, shit, I better figure out hydrostatic pressure. All right, I'll see you in the next with an example problem.